Section: Introduction. In this section, we discuss the impressive abilities of large language models, LLMs, and multimodal LLMs in various fields such as software engineering, medicine, and finance. Recent advancements in computing power and technology have allowed these models to be trained on larger datasets and to handle longer contexts, which is the maximum amount of information they can process at once. For instance, the classic novel Moby Dick, which has just over 300,000 tokens, could fit into the 2 million token context of the Gemini 1.5 Pro model nearly 5 times. Most books and series have fewer tokens than the longest context windows available in these models. Having a longer context can enhance performance, especially in many shot-in-context learning, where we can provide hundreds or thousands of examples to the model. This capability opens up a wider range of applications, such as retrieving legal documents, conducting academic research, and solving complex problems. The ability to manage large amounts of information, similar to multiple full-length novels or numerous academic papers, makes these models particularly effective for such tasks. However, the rapid development of longer context models has outpaced our understanding of how they utilize this context. Current benchmarks are inadequate for assessing their performance. We identify 3 main limitations in existing research. 1. Performance saturation. Many benchmarks focus on simple retrieval tasks, where top models achieve near-perfect scores, leaving little room for improvement or insights. 2. Limited context length. Most benchmarks evaluate contexts under 100,000 tokens, which is far below the limits of leading LLMs. 3. Lack of granular insights. The use of real documents and aggregated metrics makes it hard to identify specific trends, aside from the general observation that performance declines as context length increases. To address these gaps, we designed a series of challenging retrieval-based experiments with varying difficulty levels, testing context sizes up to 900,000 tokens. Our experiments include novel tasks that require following linked information across the context and retrieving final values. We also explore a more complex version that involves tracking multiple threads of information at once, assessing whether the models can handle this complexity. We evaluated 17 LLMs on these tasks and found that performance tends to decrease with longer contexts. Additionally, we discovered significant differences in how models tokenize information, leading us to propose a new metric for effective context limits tailored to specific tasks. In summary, our main contributions are: 1. We introduce challenging multi-step threading and multi-threading retrieval tasks and evaluate 17 leading LLMs on them. 2. We demonstrate that longer contexts reduce retrieval performance for simple tasks, while the number of concurrent queries has limited impact on stronger models. 3. We find that many leading LLMs are quite thread-safe, maintaining performance despite multiple queries. 4. We compare tokenizers, revealing notable differences in token counting. 5. We propose a configurable, task-specific effective context limit metric. In the related work section, we note that evaluating the long context capabilities of LLMs is a growing area of research. Many studies focus on long document understanding tasks, where performance generally declines as context length increases. While these benchmarks are valuable, they often explore only smaller context lengths, typically under 100,000 tokens. Although using real documents adds realism, it complicates performance analysis due to the need for timely annotation and curation. Other studies have examined more abstract retrieval tasks, which provide clearer insights but may lack real-world relevance. We aim to fill these gaps by evaluating our complex needle threading tasks across context lengths up to 630,000 tokens, providing a detailed analysis of the results. Section Summary. In this section, we highlight the impressive capabilities of large language models, LLMs, and their potential applications with longer context windows, which allow them to process vast amounts of information. We identify limitations in current benchmarks for evaluating long context understanding and propose a series of challenging retrieval tasks to better assess the performance of 17 leading LLMs, revealing that longer contexts can hinder retrieval performance while demonstrating that many models maintain thread safety across concurrent queries. Section: Tasks. In this section, we focus our experiments on abstract tasks that use synthetically generated data. By opting for synthetic data, we achieve three main benefits. First, we avoid the high costs associated with curating and annotating question and answer pairs. Second, we ensure that our data is of high quality and free from noise. And third, we gain precise control over the sequence length and other task parameters, which allows us to directly influence the difficulty of the tasks. The abstract nature of our setting minimizes natural language semantics, helping us isolate experimental variables and derive insights that are closely tied to the context window parameters. For our experiments, we utilize string serialized JSON objects that contain key-value pairs of random unique identifiers, UUIDs. Each UUID is a unique string made up of 32 characters. The prompts for each task follow a specific format, which includes a task description and the corresponding values. We outline our long context understanding tasks in the following subsections, accompanied by schematics for each task. We conduct our experiments on sets of haystacks of varying sequence lengths, where each haystack consists of key-value pairs. In the single needle task, our goal is to find the value corresponding to a single specified key at fixed depths within the haystack. For the multiple needles task, we aim to retrieve values for a specified set of keys, ranging from 2 to 25. We test two placement methods: random sampling of keys and clustered sampling, where subsequent keys are chosen from adjacent positions. The conditional needles task extends the previous one by retrieving values for keys that match a specific criterion, which we create by altering a character in the target keys. In the threading task, we select a subset of indices from the haystack and create a thread by replacing keys with their corresponding values, aiming to find the final value at the end of the thread. We explore different thread lengths and directions, including forward, backward, and random. In the multi-threading task, we modify the haystack to include multiple threads and determine the final value of each thread based on the starting keys. Lastly, in the branch threading task, we introduce branches at each link in the thread, allowing for multiple possible continuations at each step, with the goal of finding the final value of the longest thread. For the single needle task, we assess the model's ability to accurately retrieve values at fixed depths in the haystacks. Our results show that while models perform well with shorter contexts, their accuracy tends to decline with longer contexts, indicating a smaller effective context limit for most models. Notably, GPT-4o and JAMBA 1.5 Large maintain perfect accuracy throughout. The heat maps reveal that accuracy often decreases towards the middle of the context for most models, supporting our findings. Section Summary. In this section, we focus on abstract tasks using synthetically generated data to ensure high quality and control over experimental parameters. We outline various tasks, including single needle, multiple needles, conditional needles, and different threading variations, to evaluate model performance in retrieving values from structured data, revealing insights about effective context limits and retrieval accuracy across different models. Section: Multiple needles. In this section, we explore the capabilities of large language models, LLMs, to retrieve values for multiple input keys from a set of key-value pairs. We test the models with input keys of 1, 2, 3, 4, 5, 10, 15, 20, and 25. Our results, averaged across all input sizes, show a similar trend to the single key retrieval task, where performance declines as context size increases. However, the drop in performance is sharper here, with some models falling below 20% accuracy as they approach their context limits. This indicates that the effective context limits for retrieving multiple keys are shorter than for a single key. Notably, GPT-4o performs exceptionally well, achieving near-perfect scores. The heat maps for Gemini 1.5 Flash reveal that the arrangement of keys does not significantly affect retrieval accuracy, while context length has a much greater impact than the number of keys for stronger models. Next, we examine the conditional needles task, which assesses the retrieval of values for unspecified keys that include a specific character. We observe a similar trend to the multiple needles task, with a sharper initial decline in performance at shorter context lengths, leading to lower overall scores. The heat maps indicate that the arrangement of conditional keys significantly influences retrieval accuracy, with better performance when keys are clustered rather than randomly placed. Additionally, performance decreases with an increasing number of keys when they are randomly placed. We then shift our focus to threading, where we test the model's ability to retrieve final values from threads of varying lengths. This task introduces directionality, as the position of thread pieces in the context matters. Our evaluations show that average accuracies are lower for this task due to the complexity of following threads. For many models, accuracy drops to nearly zero at higher context lengths. The heat maps reveal that performance declines with both increasing context and thread lengths, and that models generally perform better with forward-moving threads compared to backward ones. We extend the threading task by adding multiple threads for simultaneous retrieval. We test various thread lengths and directions, and our results indicate that models maintain performance even with additional threads, suggesting they are thread-safe. For instance, Claude 3.5 Sonnet shows no performance drop with up to 25 threads, while GPT-4o and Gemini 1.5 Pro exhibit a gradual decline. Finally, we aggregate the performance metrics across all tasks to compare the models directly. Our findings indicate that the best model varies with context size. GPT-4o excels in smaller contexts, while Gemini 1.5 Pro performs best in longer contexts, and Claude 3.5 Sonnet leads from 2.5 to 32,000 tokens. Overall, closed-source models consistently outperform open-source models. Section Summary. In this section, we evaluate the performance of language models in retrieving values from key value pairs across various tasks, including multiple needles, conditional needles, threading, and multi-threading. We observe that while models like GPT-4o excel in single and multiple needle tasks, performance generally declines with increased context length and complexity, with closed-source models consistently outperforming open-source ones. Section: Effective context length. In this section, we discuss the effective context length. We observe that across all tasks, there is a trend of reduced performance as the context window increases, indicating that the models struggle to utilize larger context sizes effectively. Essentially, there is a limit to the context size beyond which the models cannot reason or retrieve information reliably. To address this, we propose a metric for effective context length tailored to each task, using detailed data from our experiments instead of just calculating an average. We create a dense grid of points based on two main experimental variables and interpolate the average accuracy at each point. We then identify a contour that corresponds to a specific accuracy threshold, which we set at 75%. This contour marks the effective boundary, beyond which retrieval becomes unreliable. For the single needle task, we take the lowest value of this contour to ensure our metric is not influenced by the position of the context. For other tasks, we use the contour value at a specific point on the x-axis, such as when the number of needles is 10 or the thread length is 5. We provide example contour plots and a table with the calculated effective context length metrics for each task. Since there are differences in tokenizers, we base our metric on the number of characters in the input rather than the token count. Our findings reveal that even for simpler tasks, most models have an effective context length that is significantly shorter than their stated context limits.